Now let's calculate the net force acting on one of the faces of the triangles. So just as a quick reminder, what we were looking at was a roughly planar triangle, whose one end we tied to an axis, which is perhaps pointing in the z direction. So imagine that this is the triangle is in the xy plane, and I'm going to use the same color for the xy plane. So that's the xy plane. And then this axis of rotation is along the z direction. So we have sort of imagine a sandwich box whose one tiny edge we've tied to a vertical axis, which is along the z direction, and the z direction happens to coincide with the direction of gravity. So let's calculate the net pressure or the net force which will be exerted by a fluid column, right? So we've imagined that each of these sides has a height h, which is very, very small. So maybe so that you can roughly approximate it as a planar, but not quite. There is a finite height. Okay. So let's calculate the net force being exerted on one of these faces. Now, if I look at a vertical column in this manner, and I'm just going to exaggerate the drawing. So let's say this has a height h, and at the top of this column, which is exposed to the atmosphere, the pressure is P naught. Now, as we go down the depth, and I'll refer you to a video where we talked about how the gradient of pressure aligns with the direction of gravity. So as we go down the column, perhaps to a depth of z, and we consider a tiny infinitesimal rectangular element at this depth, perhaps the depth of this tiny rectangular element is dz, and the side of this triangle has a length a, then the net force acting on this element by the pressure being exerted by the fluid column would be given by force is pressure times the area of this element, right? Now the pressure at this depth is P naught plus approximately rho gz. That's approximately the pressure at this point. The net force is the pressure times the infinitesimal area of this rectangular element, which is A, that's the length, times dz, A dz. So when I plug this pressure into this expression, I'll have the infinitesimal force on the segment is P naught plus rho gz times A dz. And we can now integrate the total force in order to calculate the total force being exerted on this wall by the fluid column. We can integrate this entire expression when the depth goes from 0. So this is z equal to 0, and this is z equals h. As it goes from z equals 0 to z equals to h. So that will be the net force on face A. So maybe I'm going to write force on face A. So the net force is, and you can just do, this is an elementary integration. So we have P naught A dz. So that's P naught A, and then the integral of dz would just be h minus 0. So that's just h. Plus, we have this additional term, which is rho g. The integral of z is z squared by 2. And we have rho g A z squared would just give me an h squared. So that's the net force being exerted on this vertical column. Now, by symmetry, we can argue that this force will be exerted at the center of mass of this particular sort of face. And perhaps we can just pick out this point here, which lies at a depth of h by 2 and at a location a by 2 to capture or encapsulate the net force being exerted on this column. So as a simplification, since the height is very, very small, we're assuming that this h is very small, so that it's roughly a planar triangular box, but it has some finite depth so that you can fill some water in it, right? So the net force will be exerted at, say, roughly h by 2 and at a distance of a by 2. So that's the location where the net force, we can approximate that the net force is being exerted at this particular point. Now, there's one interesting feature which I want to point out about this expression and this system that we're considering, that the force being exerted on a side of a triangle is proportional to the length of that side. So if I rewrite this expression in a different way, see, you'll notice that the force being exerted on face A, right, or is equal to P naught H. I'm just going to take these terms as separately. So P naught H plus rho G H square by 2 multiplied by A, and that's the dimension of the side of the triangle. Whereas this particular term in round brackets is something which does not depend upon the side of the triangle. And so this particular expression will be the same for all the three faces of the triangle that we're considering. So in a nutshell, if I have a triangular system like this, which has lengths A, B, and C, the force that will be exerted on this face will be normal to the direction of the face. Now remember that this face if this is the x-axis and that's the y-axis, it has one side along the x-axis. This depth is along the z direction, right? That's the height of the column. That's along the z direction. So therefore, the normal direction to this would be the y direction, right? So the force will be exerted in the y direction, or rather the negative y direction, because of the way we've labeled the axis. So the net force will act at the midpoint towards the negative y direction, and this force will be proportional to the length of this particular side of the triangle, right? Likewise, the net force on face B will be proportional to B, which is the length of this side of the triangle. And the net force on face C will be proportional to C, which is the third side of the triangle. So in a nutshell, what I can say is that force on face A, if I were to write it sort of introduce a constant of proportionality, which will be given by this expression. Let me just call that P. That will be the constant of proportionality. So we can say that the force on face A, or the magnitude of force on face A, will be P times A. The magnitude of force on face B will be P times B, and magnitude of force on face C will be P times C. And this is the interesting feature which we wanted to bring out, and that's the reason why the pressure distribution along the length, along the height of the sandwich box is important, because that gives us an expression for a force which is proportional to the length of the sides of the triangle, right? Now what we need to do is write down these forces in their vectorial notation, and from there calculate the net torque being exerted around the axis of rotation, or around this pivot point O, and the net torque being exerted around this axis of rotation. So we'll do that in the next part of the video when we'll complete this discussion. Thanks for watching.